Do it on your phone. Use your wireless cellular data. Your phone isn't working right now. You boys, I tell you what, get to school on. I'm going to yell like Coach Kelso yelled. Get to school on time and take care of your daggone business. I'm tired of messing with y'all. Okay? It's easy. You get your butt up on time, you get here early, and you quit being tardy. Now I feel better. Coach Kelso's got the moves, man. I can't let him be the only one having fun this morning. No jokes, though. Y'all get here on time next time. All right, so now that I've shared my screen with you guys at home, we got our recording going. Yesterday we wrapped up our lesson on solving systems by graphing, okay? And so today we're going to move on into a little bit more of a reliable technique called substitution, right, Joseph? We're going to like substitution. It's going to work a lot quicker and a lot more accurately than graphing. Now, graphing is good. It's got its benefits, but we said before it's time-consuming and it can be perhaps inaccurate. So what I want us to do is I want us to work through these two examples, solve them out quickly, warm up for you by graphing. And then also remember, you guys have Delta Math assignment that's due today at 3 p.m. about graphing. If you have not finished, the vast majority of you have already, by the way, I checked. But if you have not finished that, make sure you get her done before 3 p.m. today. These are a couple of examples just like that. And what we're going to do is after we solve these using graphing, I'm going to use these two examples. I'm going to pitch the notion of substitution to you, and you're going to say, wow, substitution is way better than graphing, Coach Morgan. Thank you so much. All right, but if you're watching at home after the fact, or if you guys are in my 7th period and you're watching this recording today, you can kind of pause the video and save yourself a little bit of time while you're working through this, and then push play once we resume with the examples. So Nick, this will be where we're graphing. So get that y by itself, figure out the slope and the y-intercept, and go to town on that graph. And Hogan, remind us about the graph. What are we looking for?
Looking for
the point of
intersection.
Intersection. Very good. We want to find where do those lines cross. And Luke Hecht, do all lines always cross? No, sometimes they are, what's that P word? Parallel. And Cash Johnson, if they're parallel, they're going to have the same whats? They'll have the same slope and different y-intercepts. All right, so I'll hush up. You guys keep working. Give you about 2 or 3 minutes per problem here to graph these out. William, didn't I give you a pencil yesterday? You know what you did? Oh, no, I gave him a pencil too. And you left it laying on the ground under that chair, and I went over and scooped it up, and I thought he's going to ask for that again tomorrow. Sorry, Calderoni. I hit the ceiling, and then it bounced on the floor and landed in your bag. William, keep hold of it. If somebody gives you something, don't lose it so quickly, son. Do what? All right, now those of you that are watching what I've been doing, You might notice that with that first line, I got y by itself. Okay. Subtracted 2x, divided everything by 3. So Ashton's going to tell us what we know about that first line in blue.
The y-intercept is negative.
All right, very good. Y-intercept is -2. And what else? Excellent. So down 2 and to the right 3, that's our slope. Or, if I'm out of room, I could also go up 2 and to the left 3. Very good, very good. 1, 2, 3. I like 3 points. Just makes my line a little bit more accurate. There we go. Okay, now what kind of, does anything stick in your craw about that second one, about the one in orange? What do you not like about that one? Sebastian? Yeah, -17 halves. In fact, when I did that, I had to go back and double check to make sure I didn't screw anything up. -17 halves is, what is that, -8.5?
Yep.
Okay, that's an in-betweener. And what we're going to get comfortable with today is having an answer, or at least going through a process where we're dealing with fractions. That is okay. 5, 6, 7, 8. So 8.5 down here on the negative y-axis, and then a slope of 3 halves. So going up 3, watch this. 1, 2, 3 over 2. All right, and then up 1, 2, 3 over 2. So in my graph, it kind of looks like they cross at what point? 3, -4. Did anybody else get that value? Well, 17 over 2 is the same thing as 8.5. Yeah, so I just went down 8.5 because it was -17. I went down 8.5 and put my point there. And did you guys see? I don't know if you zoom in a little bit, make it easier to see. Do you see those little orange dots where I was counting my slopes just in between? Because I didn't have tick marks to count by since it was an in between value. So literally all I did was I just said, okay, let's go up 1, 2, 3 units, and let's go over 1, 2 units, and then up 1, 2, 3, and then over 1, 2. And it looks like my lines cross at 3, -4. I think that's pretty decent. Let's verify. All right, and let's see here. Oh, I don't know. Santiago, tell me how to verify. We plug in 3 and -4 for the x and y. So 2 times 3 is 6. 6 minus 12, that checks out. And then 3 times 3 is 9. -4 times -2 is what? What's that? 8. 9 and 8 make 17. Ho-ho! It checks out and we look good. Notice that the checkpoint, that last step, didn't take so long. We're just doing a little mental arithmetic. Cover that nose up, please. We're just doing a little bit of mental arithmetic. Now, I don't know if you guys have had time to finish the second one. What answer did you get? -1, -1? Does anybody concur with Cash's answer? Well, let's see. I don't know. If we plug in -1, that's going to be -5 plus 2. That equals -3. I like that. If we plug in -1 for y, so that's -6. -1, so that's going to be plus 10. -6 plus 10. Ooh, sorry. So close. And yet so far. I tell you what we'll do. Just for time's sake, I don't want to spend too much time on the graphing. Why don't we let this be our first example for substitution? All right, let's do that. Call a little audible here. Now, could you have solved this out by graphing? Probably, but heck, I kind of want to get into the meat and potatoes of today's lesson. So here's an example for you. Write this one down if you don't have it written down already. If you've gotten a little bit of the graphing done up to this point, you can try and finish it while we're kind of going through this. You multitask. All right. But what I'm going to teach you guys here is I'm going to give you a step-by-step process. Okay. I want you to write down those steps for solving this system using substitution. Okay. You might realize, I don't know if I've said this, I'm dressed up. I got a suit on today. I'm going to a funeral later, and I'm going to have to miss 7th and 8th period. Okay. And so I sent in a what? I sent in a sub request. So for my 7th and 8th period today, a substitute is going to come and take my place. I think Coach Dunlap, for example, in 7th period. So if you're watching this, in 7th period. Coach Dunlap, I think, is y'all's sub, right? And so what he's going to do is he's going to stand in place. Coach Morgan's out. Dunlap is in. Okay? Now, substitution works that way when you're plugging and chugging values. Like if I said, hey, evaluate this. Well, heck, even in the last example, when we were plugging in our answer, we were using substitution. We replaced X with whatever the X coordinate is. That's how it's going to be here. Okay? So first step in this process, I'm a step-by-step kind of guy for this. First step, I want you to pick a variable in one of the equations to isolate. All right, isolate means get it by itself. So isolate one of the variables in one of the equations. All right, now here's a little piece of, teacherly advice. If I were you, I would pick the variable that has a coefficient of 1, if there is one. Okay, if I were you, I would try and pick the variable that has a coefficient of 1. Now, that's not always the case. That's not always going to be happening. As in this example, it doesn't happen in this example. Okay, but if you can, try and pick one where there's a coefficient of 1. It makes your job a little bit easier. Okay, so we're going to pick either X in the first equation, Y in the first equation, or X in the second equation, Y in the second equation. We're going to get it by itself. I'll let Quinn Page, you can be our picker. Which variable and in which equation? He wants to get Y by itself in the second equation. All right, giddy up. Here we go. So can you, Justin Bowers, get Y by itself? Do my 2 steps. What do you want to do first? We're trying to get Y by itself. Why don't you leave Y there? All right, let's add 10x both sides. So we got to have 6y equals 10x plus 7. All right, and then let's kick it back to my other Bowers. Drake, what's your next step? Getting Y by itself. What do you want to do now? Divide by 6. Very good. So we divide by 6. We got Y equals 10x plus 7. I'm just going to keep the whole right-hand side divided by 6. Okay. So what that means, remember, Coach Morgan gone, Coach Dunlap in his place. So what that means is that Y is the same thing as 10x plus 7 all over 6. Wherever I see Y, I can plug that expression in. Okay. Now here comes step 2. Plug that expression into the, watch this, I'm going to underline it, other equation. Okay, so Quinn chose to get Y by itself in the second equation. Bowers times 2, they got Y by itself for me. And we got our expression, and we're going to plug it back into the first equation now. Because if you plug it, listen to me, if you plug it back into the equation from which it came, that's like a dog chasing his tail. You're not going to get anywhere. Things will cancel out. You'll get something stupid like 6 equals 6. You can't do anything with that. But if you plug it back into the other equation, watch what happens. All right, plug it back into the other equation. 5x plus 2 equals 3. Now, instead of 3y, what am I going to plug in place of y? I'm going to plug in place of y, that expression right there, 10x plus 7 over 6. 10x plus 7 over 6. Okay? So instead of 5x plus 2 equals 3y, I got 5x plus 2 equals 3 times that expression. All right, and now I'm going to solve. Solve that equation. Okay, now you might notice that equation is now in terms of one variable, isn't it? The only variable that's in that equation is x, so I should be able to solve for x. And this is where you guys snatch hold of it and you run with it. Nick, cover your nose up. And this is where you guys have practiced for the last several months, right? To where you can solve for a variable. For instance, I might want to say 3 over 6 simplifies down to 2. So this is 10x plus 7 over 2. And then I might want to times both sides by 2. So it becomes 10x plus 4 equals 10x plus 7. And then I might want to subtract 10x from both sides. And I wind up with 4 equals 7. Now, what do you think about 4 equals 7? JT? That's not true. That's nonsense. So what we have done is we've run into what's called a contradiction. This is called a contradiction. And I'll be honest with you, I'm a little bit displeased because I randomly picked one from the warm-ups. And this is one of those weird ones, right? Where the lines are what? Parallel. The lines are going to be parallel. I just happened to pick the one that Degum had parallel lines. I should have realized. But that's okay. If you reach a contradiction, you throw on the brakes and you say, well, stop. There's no way that 4 could equal 7. Therefore, there's no solution. So we're going to stop and we're going to say there's no solution. What are those 2 lines? Actually, if we were going back in the warm-up and we're going to graph those 2 lines out, they'd be parallel lines. We'd say, hey, there's no solution there at all. Okay. Let me go back to this example, though. Why did I times everything by 2? There's a times by 2 on the right that canceled out that fraction, and therefore there's a times by 2 on the left that balanced that out. So that's where that 4 came from, and that's why we did that. But hey, look, we're versatile, and we're gonna roll right over that speed bump. Coach Morgan's first example was a Degum contradiction, parallel lines. Let's look at another example. We're going to use these same steps. Actually, let me go ahead and we're going to pretend like, let's say when you were solving this equation, let's say you actually got x equals, I don't know what, something. The 4th and final step there is to plug that number in to solve for the remaining variable. For the remaining variable. In other words, let's say I just found, I'm going to make something up, like x equals 7. Let's just say we found x equals 7. I'm going to take that, and I'm going to come over here, and I'm going to plug 7 in for x to see what y equals. Because what is the solution, William Kreitz, to a system? We're trying to find that point of intersection, and a point has 2 coordinates. So like if down here, if we found, like x equals 7 or whatever, I don't know. And I come over here and I plug that in, and let's just pretend like y equals -1, then I would say, oh, my answer is 7, -1. That's my ordered pair. Okay, so this was a rare case where the lines were parallel. Let's look at another example. By the way, there's your step-by-step approach that we just walked through. Okay, let's try this one again together. So first step is to isolate a variable in one of the equations. And Colton, I'm going to let you pick which variable would you like to get by itself. And remember my little suggestion, there's actually a good one on this example. The y in the second equation. I'm glad you said in the second equation. Because look, well, all I have to do is add y to both sides, subtract 8 from both sides, and it's easy peasy. Look, y equals 6x minus 8. Okay. That's your first step, right, William? We get one of the variables by itself in one of the equations. Now, Ryan Jeffers, what do you want to do with that expression? Y is the same thing as 6x minus 8. So where do I plug 6x minus 8 in?
Into the first equation.
Very good. I'm going to take that expression, and wherever I see y, I'm going to substitute it in to that first equation. All right? And that's going to make me a nice new first equation. 4x plus 2, instead of 2y, it's going to be 2 times 6x minus 8. Okay, so we took the y variable, isolated it in the second equation, we plugged it into the first equation, and now we can combine like terms and we can solve. This is where you guys are off to the races and you're running with it. Okay, this is where you go ahead and Jackson says, hey, distribute that 2. We get 4x plus 12x minus 16. And then we say, hey, let's combine our x terms. What do we get? 16x minus 16. Add 16 both sides, we get 20 over there on the right side. Divide both sides by 16, and we get 5/4. X equals 5/4. By the way, is it okay to get a fraction as part of my answer? You're daggum right it is. All right, Wilson Webster, what do I do next? now that I've got half my answer, yeah, and we can plug it back in. This is our last little step. We could plug it back into either of the black equations, either of the original equations. But here's a little teacherly advice. I would recommend plug it back into the one where you've already got the variable by itself. You've already got y by itself. So why redo the work and have to solve for y again if we could just say, hey, let's plug in 5/4 there for x. Okay. Let's see here. 6/4. That's going to be 15 halves. 8's the same thing as 16 halves. So what's that going to be? Y equals -1/2. And that's going to be the solution to our system. 5/4, comma, -1/2. Now, somebody tell me why we're thankful that we didn't have to do graphing on that one. Will you? Speak up. But because the 5/4 is a fraction, the 1/2 is a fraction, and we don't do well with in-between values on a graph. That'd be like trying to find where they cross. Like, not that this is the graph of this system, right? But like, just pretend with me here. If these two lines crossed, like somewhere where I could not tell where they were at, like they're in between values, right? And I can't really judge super well what in between values are on a graph. The algebra allows me to find exactly what they are every time. Okay, Santiago.
There, you subtracted 8 from 15 over
Mm-hmm.
to get 16 over 2.
8's the same thing as common denominator. 8's the same thing as 16/2. So I changed 8. Did y'all notice that real quick? I changed 8 to make it have that common denominator, so it would go with 15/2. Okay.
Sorry, I must have.
That's okay, buddy. Go ahead and ask.
But like, how did you get y equals 6x minus 8?
All right. So good question here. What I did was I added y to both sides. So we had 6x equals y plus 8, and then I subtracted 8 from both sides. And got y equals 6x minus 8.
Yeah, how'd you get 6x from 4x?
No, we were just dealing with the second equation. Remember, I asked Albinetti, I said, hey, Albinetti, which equation should we get a variable by itself in?
Okay.
And he said, get y by itself in the second equation.
Okay.
All right, shall we try another example? All right. We'll do this one together. I won't make you guys try it on your own. And actually, let me get myself a little bit more room. So I intended to do 3 examples today. And the third one was going to be our special case. We just started with a special case, so oh well. All right, let's see here. Will Perrone pick a variable to get by itself in one of the equations?
X in the first equation.
Fabulous choice. Why do you think that I like his choice? Nick? Yeah, all we got to do is add 4y to both sides. It had a coefficient of 1. We didn't have to do any division. So if we can get x by itself, we got x equals 4y minus 4. That's what x equals. X is the Coach Morgan. 4y minus 4 is the Coach Dunlap. They're going to swap out. It's a tag out. Okay, so Coach Morgan's gone. Coach Dunlap comes in place. That's substitution. Into which equation should we substitute the expression 4y minus 4 for x? Drake? Into the second equation, into the other equation. Hey, let me just demonstrate for you, okay? Watch what happens if I had erroneously plugged in 4y minus 4 for x in the first equation, okay? So it's x minus 4y equals -4. And instead of x, let's just pretend like I plug in 4y minus 4. What happens there? 4y minus 4y, I got -4 equals -4. And it's like, well, duh. That's true, but where do I go from there? It's a dog chasing his tail. So don't plug it into the same equation from which it came. Plug it into the other equation. We're going to take that expression and we're going to substitute it into this other equation. Can y'all tell me what that would look like, Joseph Russell? -3 times what? Very good. -3 times quantity 4y minus 4. And then we're going to say plus 4y equals 0. And we're going to go to town on solving that equation. And I hope that when we get to this point, that you guys are like, okay, cake. I can solve that equation in my daggum sleep. Okay. So again, what we did was we got x by itself in the first equation. We plugged that in for x in the second equation, making one equation in terms of one variable. And now we're going to distribute and solve what? Negative 12y plus 12 plus 4y equals 0. Can we combine some like terms? What is that? Negative 8y plus 12 equals 0. Negative 8y equals negative 12. So y equals, what's 12 over 8? 3/2. Is it okay that I get a fraction? Say yes. Yes, it is. Okay. We're big boys now. We have moved past the land of 8th grade where all numbers always work out nice and neat and pretty. Right? We're capable now of dealing with fractions. And then I'm not done. Please don't stop right there. We want to take y equals 3/2 and plug it in and find what x should equal. And why not go ahead and use this spot over here where we've already got x by itself. So instead of 4y, it's going to be 4 times 3/2. What's that going to be? 6 minus 4 is 2. Okay, and that's going to be my, that's going to be my solution. I got 2, comma, 3/2. Hogan, you all right over there?
Yeah, it's just every single time I move my foot, I keep track.
You know what it is? I bet it's those ankle socks that you wore again today. That's probably what it is. Oh, I love busting people's chops. You know what we're going to do for you, Hogan? Just because I love you so much, we're going to put this over behind you. In no man's land. Do what?
I can't stand it.
I love me some ankle socks, dude. Just not when you're wearing dress shoes. All right. Now, earlier, we had one of those special cases where the lines were parallel. What's the other special case? If they coincide, if they're the same line. Now, look, I've noted for you that both of these examples are quote, special cases. Can you figure out which one's which? It's like my kids have been listening to this Disney Halloween CD lately, and there's this song that Mickey and Goofy sing called Which is Which? Yeah, can you figure out which of these is which?
I have a question.
Go for it, Afgar.
On the last one, how did you get x equals 10?
On the last one, we took, so you were cool on how we got y equals 3/2?
Yeah.
We took that and we plugged that in. See where I got it circled? We took the question, so for you guys at home, the question was how did we get that x equals 2? We took y equals 3/2, we plugged it in over here, and then we ran the numbers and we got down to x equals 2. So we had solved earlier, we had solved for, that we had said x equals 4y minus 4. And then we said, oh, well, if that's the case, and y is 3/2, 4 times 3/2 is 6. 6 minus 4 winds up being 2. You're looking at me like I'm a crazy person. You got it?
Yeah.
All right. Which is which? Do we know the difference? If they're parallel, they have same slope, but different y-intercepts. Okay. What do you think? First one is what? First one is overlap. Well, let's see. I happen to note that in this first one, each of these is divisible by -3. -6 over -3 will be 2x. 3 over -3 would be -1. -9 over -3 would be 3. And so what do we notice about those two lines? They're the same thing. Don't do unnecessary work. If those are the same things, here's where graphing pays off, right? This one would be, this is what its graph would kind of look like here, right? And it would be the same line, whoops, just drawn over the top of itself. So how many solutions would there be? We'd say infinitely many solutions. Now, what does that look here? You need to identify this because you might not be on your toes and you might jump into it thinking, oh, I'll just use substitution. What does that look like when we work substitution on this? Okay. Well, instead of getting a contradiction like we did in the very first example today, watch what we get. Here, I'll just get y by itself in the first equation. Can y'all run this with me here? Y by itself in the first equation, we're going to get y equals 2x minus 3. Okay, that's an expression for y that I'm going to plug into the second equation. Negative 6x plus 3 times the quantity 2x minus 3 equals negative 9. Distribute. And the 6x's cancel out, and we got negative 9 equals negative 9. Is that a contradiction? No, that's true no matter what. So in your notes, please write down that if you get something that's true no matter what, we call that an identity, by the way. If you get an identity, that's where you're going to have infinitely many solutions. There's infinitely many numbers that I could plug in for x to make that equation true. Because negative 9 equals negative 9 no matter what I plug in for x. That if you get an identity, not a contradiction, but if you get an identity, that's going to be where there's infinitely many solutions. This is called an identity because it is true no matter what. Whereas if you get a contradiction, all right, look at the last example here. Now, thankfully we've already got y is already isolated, so let's just plug that in place. In the second equation, 2x minus 5 quantity 2/5 x minus 4 equals 3. Distribute negative 5, and we get 2x minus 2x plus 20 equals 3. The 2x's cancel out, and you got 20 equals 3. What do we call that again? That's a contradiction. And so an identity leads us to infinitely many solutions. A contradiction, all right, we would say, sorry, no solution. Those lines are parallel. There's a line right there, and there's a line right there. There is no point of intersection. Graphically speaking, we could see that. All right, but if you're wheeling and dealing using substitution, and you're not paying attention, and you just continue in that mode, you don't always look to see if they're going to have different slopes or the same slopes. Just mind yourself when you get down to an identity, stop, throw on the brakes and say infinitely many solutions. Or if you get to a contradiction like we saw in our first example, or like we saw here with example 4, we just say, oh, okay, well, those are parallel lines, no solution. A vast majority of the problems that you guys get, though, are going to look like example 1 and example 2. Vast majority of them will look like that, okay? Where you actually get an ordered pair. You get a solution, okay? So tonight and on into the weekend, I'm going to have you guys working some Delta Math problems. It'll be due Monday, okay, using substitution. All right, so due at 3 o'clock today. Let's just make sure we understand each other. Due at 3 o'clock today, Cannon, we've got what?
Delta Math.
We got Delta Math homework on graphing. Due tomorrow morning at 8 a.m., we've got what? ACT practice quiz. And then due Monday, we'll have some substitution practice on Delta Math that I'll put together for you guys. All right. Now, if you have already finished your Delta Math that's due today at 3 p.m., kudos. If you have not, get your laptop out and you can work on it for 6 minutes. Nay, 7 minutes. If you have already finished your ACT, kudos. If you have not, get your laptop out, go on to Microsoft Forms and start working on that. Jacob Alprin. Louder. It's going to post Monday morning at 8 a.m. and it'll be due next Friday at 8 a.m. as well. Santiago? Yeah, it was 10 of the first kind and then 5 of the second kind. All right, you guys at home, if y'all have any questions, holler at me. And in the meantime, live Jesus in our hearts.
Forever.
All right. Thank you, guys. Sebastian, question?